Welcome to the second set of lectures for the first week of the Introduction to Data Science module, Python for Data Science. We'll be moving on with our discussion of the Python programming language by talking about data structures. So in the data course Python directory, there's a PyDataStructures notebook, and you'll want to go ahead and open that up to follow along. And in fact, I'm also going to open up the program flow notebook that we were using in the previous set of lectures when we were discussing variables and functions and iteration. And I'll come back to this notebook shortly, but let's get started with the data structures notebook. So I'm just going to clear all my outputs. So in the previous lectures, we introduced variables, and we saw that we could create different variables with different types of data in them. And we could even, this is not supposed to be here, but many times we'll want to not work with individual pieces of data, but data as a collection. For example, in the previous lecture, I had variables containing information about myself. But I might want to group this information together into a single variable so that I have all the details about me or other people all contained under one name in Python. And that's what data structures are for. They allow us to group together or structure multiple parts, multiple pieces of data or information. We saw an example of this in the previous notebook with several recipes that we were printing out for cooking different bits of food. We had a beans recipe, a soup recipe, and a bread recipe. Each of those recipes was stored in a list, just like in, our normal lives. If we were reading a recipe, there would be a list of instructions that we had to execute in order to cook the food properly. So here we have a beans recipe where we have a collection of strings contained within a list. So lists are designated by square brackets. And you just have each element separated by commas. So we have square brackets to start the list. Then we have our first element in the list, comma, the second element in the list, comma, the third element in the list, and so forth until we reach the end where we close that square brackets to designate the end of the list. So as I mentioned, let's look at an example of illustrating why we might sometimes want to work with a collection of data points rather than individual variables. So here, if I'm going to cook something, I'll need to go shopping for groceries. So I could create variables that store the name of each item that I am going to buy at the store. We have groceries A, B, C, D, and E, chicken, onions, rice, peppers, and bananas. Alternatively, I could store them all together in a list as one variable, grocery list. Let's see how these two choices, these two alternatives to each other, might impact the code that we write later on. So if we're going to buy our groceries, we might want a little program that says, maybe we're buying our groceries online, and we tell the program what groceries we want to buy, and then the program goes and purchases each one. So we have two functions here that will do essentially the same thing. It prints out buying and then the name of the item that it is buying. In the first implementation, we have buy groceries individual, which accepts 5 arguments, items A through E. And it has 5 print statements printing out buying and then each item. We also have buy grocery list, which accepts 1 argument, which will be a list of items. It then iterates through the list, and for each item in our list of items, it will print buying that item. So now that we've defined these functions, let's see what happens when we call them. We can use buy groceries individual and pass it each individual grocery variable that we defined above. And it will print out buying chicken, onions, rice, peppers, and bananas, just as we expect based on the function definition. Grocery list has the same items in the same order. And we can call that function by just saying buy grocery list and then pass that grocery list as the argument. Now, obviously, there's already been some benefits. Using a list involves much less typing and much more readable code. Here, I had to create individual variables for each item, for each argument, and then a print line for each argument as well. Whereas for the other implementation, I could create 1 variable. I still had to type out all these strings, but I was able to store them in 1 variable, which I pass into the single argument of the function, and then I can simply use iteration to pull out each item from the list. I don't need individual print statements for each item. But there's additionally a sort of hidden or less obvious benefit. This function requires 5 arguments. But what if we want to buy 6 groceries or 3 groceries? What can we do? Let's go ahead and try and buy just 3 items using this buy groceries individual function. When we try to make the function call, we encounter a type error. The type error tells us buying groceries individual, the function that we called, is missing 2 required positional arguments, item D and item E, meaning this function requires 5 arguments, but we only gave it the first 3. Therefore, the function call fails. If we wanted to fix this, we could do something similar to what we saw in the previous notebook. Remember, in the previous notebook, one of the things that we demonstrated was this exact problem. We had a print to do function with 4 arguments, and if we tried to call it supplying less arguments, we encountered the same kind of error. The way we solved that problem, or addressed it, was to set defaults for each argument. So we could do that here, saying all these arguments default to none. Now, this function call will work. But we see it still prints 5 times, but those last buying statements are just buying none. If we wanted to avoid this behavior, we'd have to go back and make even more changes. As we can see, this function is getting more and more complicated, which not only makes it more difficult to understand, but requires more work from us. Let's see how these problems are handled by the approach using a list. I can have a short grocery list or a long grocery list. In both cases, the function call works because the function accepts a single argument, the list, and then it iterates over the list until it reaches the end, no matter how long or short that list is. That means our function can easily handle grocery lists of different sizes. Even with the modifications we've made to the buying groceries individual function, we still can't do something like buy a sixth item. Here we've added a grocery F, squash. And even after setting the defaults, because we still only have 5 positional arguments, we can't give 6 arguments. Hopefully this convinces you that lists can be very useful when we're defining functions that should accept a variable amount of information. Of course, if you remember from program flow, another thing we saw was a star args implementation. But star args is exactly an implementation using a list. Notice when we use star args to accept a variable amount of positional arguments, that gets stored in a list called args, which we then iterated over. So this implementation is a list implementation. Now that lists are one among several different data structures that can be used to contain or collect data into a single variable. There's a variety of data structures in Python. The ones that we'll be discussing in this notebook are known as containers, since they store different objects together in memory. If you want to learn more about containers, there's a link in the notebook to a Stack Overflow post that explains in more detail what containers are. In data science, we'll often use containers to group together bits of data that logically belong together, such as a quote-unquote data set. So often we'll represent data sets in the form of a data structure, such as a list, a tuple, a dictionary, or a set. We'll be talking about each of these data structures in the course of this notebook. At this point, you should pause the video and complete the following exercise. Think to yourself what kind of data can naturally be represented by a list, and what it might look like to try and make a list of lists. Once you've completed this exercise, unpause the video and I'll share a solution for creating a list of lists. Okay, so hopefully you've completed these exercises. To make a list of lists, we first create a list by opening a set of brackets. Then, we simply do it again. A list can contain other lists. And each list is created using the same syntax for list creation. We simply have our data separated by commas contained within square brackets. So this is a list containing 2 lists. Note, when I created this variable, briefly, as I was typing, the word list lit up green. List, just like return, print, and def, is a protected word. So you should never create a list by saying list equals A, B, C, or anything else. As a reminder, you should never assign a value to a word that is highlighted in green, because such words are protected words in Python that have important meaning to the Python interpreter. And by overwriting the meaning of this word, you may interfere with the normal functioning of the interpreter. Let's continue to explore lists. Lists are sort of the most basic data structure in Python. And many of our discussions of other data structures will be relative to lists. We'll use a list as our sort of baseline for thinking about other data structures. As we've seen, lists are contained within square brackets wrapped around the data we want to contain. Earlier, or so far, we've been creating lists by entering data directly into the square brackets. But we can also create lists from variables. So for example, when we had our groceries earlier, we could create the grocery list by writing out the same set of strings in the list, or we could create the grocery list by having a list of the variables that we had previously defined. In both cases, we get the same result. So thus far, we've worked with lists that contain text or numbers, but lists can contain a mix of data types. Here we have a list of integers and a list of floating point numbers, but we could also have a mixed list containing integers, booleans, strings, and floats all together in the single list. Therefore, we say that lists are heterogeneous, meaning they can store different types of data. This is in contrast to homogeneous, meaning it can only store a single type of data. Eventually, we'll encounter some homogeneous data structures in Python, but many data structures are heterogeneous and can store a variety of data types all at once. As we've seen, we can even put a list inside of a list. None of these lists must be of a single type. We could have a list containing a list, a string, numbers, and even a list inside of a list that contains yet another list and a string. This is a rather confusing list, and you probably wouldn't want to work with something like this. But it just goes to show that lists are extremely flexible in terms of what they can contain. Once again, we call this property heterogeneity, or we describe the list as heterogeneous. This is one of the major defining properties of a Python list as a data structure. You may have also noticed that when we created the list, the order in which we entered the elements is the order in which they were printed out when we printed the list. Therefore, we say the list is also ordered. This is another major property of the list data structure. We'll eventually encounter data structures that are unordered, where the way in which the elements are printed out is not the same as the order in which we put them in. Because lists are ordered, we can retrieve data from the list based on its position. So for example, our grocery list has chicken, onions, rice, peppers, and bananas. We can retrieve the element in position 2 and print it out. That element is rice. Note that position 2 is the third element of the list. In Python, the first element of the list is in position 0. Therefore, sometimes people say Python lists, or Python in general, is 0 indexed. The beginning of any data structure is indexed at the position 0. To retrieve items from the list based on position, we use square brackets after the name of the variable. We can additionally retrieve a sublist or slice of the list. In the square brackets, when we're retrieving items by position, we can specify a range of items to collect. Here, we'll collect the items between position 1 and 4. The item in position 1 is onions. The item in position 4 is bananas. Notice bananas is not included in the output. So Python goes from 1 up to, but not including 4. So we get 3 items: onions, rice, and peppers. We can also use a shorthand for slicing until the end of the list or from the beginning of the list. Here, we slice the list from the 3rd position to the end. Position 3 is peppers. So grocery list 3:nothing will start at position 3 and slice out everything until the end of the list. So we get peppers and bananas. Similarly, if we slice grocery list :3, it will start at position 0 and advance until position 3. So we start with chicken, onions, and then rice. And when we get to position 3, we stop. Lists also have a length, which I've used here in this slicing syntax. The length of this grocery list is 5 because it has 5 elements in it. Python also allows us to use negative indexes, where we count from the end of the list backwards. So if we want to retrieve the last item in the list, we can ask for grocery list -1. This is also useful if we want to slice out, for example, the last 3 elements of the list. We can slice from position -3 until the end. The last element in the list is bananas. The item in position here we have a slice containing the last 3 elements of the list. We can also choose a different step size other than 1 for slicing the list. Here, we slice from the beginning to the end using a step size of 2. We could even step through the list backwards by setting a step size of a negative value. Here, we'll go from the 4th item up to, but not including the first item, or the item in position 1, the second item technically, and we'll print them out in reverse order. So for the first example, we start at the beginning, and then we skip. Let's just print out grocery lists so we have a reference. So we started at chicken, then we advanced 2 to rice, and then we advanced 2 again to bananas. So we went from the beginning to the end with a step size of 2. In this second example, we started at position 4, which is the end of the list, bananas, and we went up to, but not including position 1, walking backwards. So we got bananas, peppers, and rice. We've also seen we can retrieve items from a list using iteration, or a for loop that steps through the list. Here, we can pop items out of the grocery list by saying for item in grocery list. And then with each step of the iteration, we can do something with that item. We'll see this syntax repeated again and again throughout the course. The iteration proceeds through the list in order, since lists are ordered. Item takes on each value in order one by one as the iteration proceeds. While we could also loop through the grocery list by using an index to step through the grocery, or to step through the positions in the list. So we could say, for instance, for I in range from 0 to the length of the list, taking steps of size 2. And then we could print out both the index and the grocery list itself indexed by that position. This gives us a similar output to what we saw before when we sliced the list using steps of size 2. However, the slice returned a list, or sublist. Here, as we iterate, we're picking out individual items by position. So we get the items one by one. In Python, we generally prefer this syntax. It's common in other languages to use indices for looping through data structures. But in Python, we iterate through the data structure directly most often. This range function creates effectively what is a list of integers between the first and second argument, using the third argument as a step size. Note, it doesn't exactly return a list. It returns a range object, which is what's called a generator. We'll talk more about generators in the future, but we can examine what's contained within the generator by turning it into a list. If I just put wrap list around each of these, it will convert this range object into a list. And then we see that this first range object has numbers from 0 up to, but not including 10, taking a step size of 3. This range object counts from 104 down to 100, taking a step size of -1. By default, range will start at 0 and count up to the number specified using a step size of 1. Usually, we want to count by ones, and often we want to start at 0. So you'll often see range with just a single argument specifying the upper bound of the range. Here, for range 5, we get the numbers 0 through 4, counting by ones. We can not only use indexes to slice into a list or retrieve items by their position, but we can also use those indices to update or replace items in the list based on their position. So if we start out with our grocery list from before, if we wanted to buy oranges instead of bananas, we could access the list at position -1 and reassign that element to be equal to oranges. We could even do this with a slice of the list by indexing into a slice and setting it equal to a new list. So as a result of taking grocery list -1 and setting it equal to oranges, we see at the end of our list where bananas used to be, it's replaced by oranges. Then we take that list and replace items 1 and 2 with carrots and couscous. So onions and rice get replaced with carrots and couscous. Because we can modify lists in this way, we call them mutable. In computer science, modifications of an existing variable are called mutations. The variable mutates as we change its state. So another major property of lists is that they are mutable. We'll also encounter Python data structures or types that are immutable, meaning that once we create them, we cannot update them in the way that we have here, or at all. If we want to change them, we would have to reassign them in their entirety. Another mutation we can make to a list is to add new items. So here we have our grocery list that we started out with in the beginning. And if we wanted to add more items, we can append an item. So here we have our grocery list, and we can add squash to it by saying grocery list.append squash. Append is a function that belongs to the grocery list. Such functions are called methods. We'll talk more about methods in the future. But basically, there are certain functions that we can call directly from a list object. Those functions interact in some way with the list and therefore are bound to it. But otherwise, they work as normal functions. We call them using parentheses, and inside the parentheses, we pass in any arguments we want to specify. We can view some of the methods of an object by using the dir function on the object itself. This shows us a lot of information. Some of it is somewhat irrelevant or meant to be private and not used, such as these funny methods that are surrounded by double underscores. Also, not everything shown here is a method. We'll discuss more about what these things are in a future lecture. But for now, we can see that the list has this append method, as well as some other things that might be methods that we may examine very soon, such as append, copy, extend, and pop. Let's try to append more items to our list. What if we want to append multiple items to our list? When we try to append a list to our list, we end up with a list in our list. Append enters one item into the list, one object. A list is a single object, and so append enters it into the list as a single entity, a single object. Since lists can contain lists, nothing prevents us from doing this. If we want to add multiple items, instead of using append, we should use extend. So here, I reestablish my list as it was before I appended bread and salt. And instead of appending bread and salt, I'll extend the list with this new list. Now, all the elements are contained within the list as simple strings. This is similar to if we had said for new item in bread, salt. I'll just re-initialize initialize this list up here. Grocery list, append new item. As we can see, these two implementations are effectively the same. However, grocerylist.extend is much more concise than this for loop. Just as we can add items to a list, we can remove them. If we want to delete an item from the list, we can use the del keyword, which is short for delete. This will delete the last item, item -1, in the list. We see salt has been eliminated. Often, we won't just want to remove the item from the list, but we'll want to do something with it. We'll want to empty a list item by item and do something with each item as we pop it out of the list. For this, we can use the pop method. Pop will automatically remove the last item from the list. Here, the last item is bread. The result of pop is to return that last item and remove it from the list. So when we print the result of popping the list, we see bread popped out, and it is no longer part of the list. We can pop from other positions by specifying the index of what we want to pop out of the list. By default, it pops out the last item in the list. Another mutation that we can make is to sort a list. So currently, our grocery list is ordered in the order in which we entered items, but it's not ordered alphabetically. So we could sort it alphabetically by doing our grocery list and dot sort, which calls the sort method of our list. And now our list appears in sorted order. Keep in mind, since we last evaluated the list or printed out the list, we have removed items, so some items have gone missing. But our list is now in alphabetical order, B-O-P-R-S. Now, I want to make one more comment about, let me first sum up. So, we introduced Python lists, which are containers that can contain mixed data types. So lists are heterogeneous. The order in which we enter the data is the order in which they are contained within the list. So the list is ordered. And we also saw that after the list is created, we can manipulate individual elements within the list and mutate them. So the list is mutable. This fact that it's heterogeneous and mutable allows for a lot of flexibility in using the list for various purposes in our programs. However, because they are mutable and can change, we need to be a little bit careful, because as our program proceeds, we may change our list and put our list into a state that we don't expect. So mutability comes with a certain element of danger. At this point, I'd like to ask you to pause the video and complete the following exercises. After you've completed the exercises, you should unpause the video and I'll share my solutions to them. Okay, so for exercise 1, we're asked to make a list of 10 elements and select only the last two elements. So one easy way to make a list of 10 elements is to make a list out of a range object with the numbers 0 through 9. So here's that list. And if we want to select the last two, we'll take a slice of that list using square brackets, and we'll slice from the second to last element, -2, until the end. So I'll put a colon and then nothing to show that I want to slice to the end of the list. So the last two elements are 8 and 9. And that's exactly what I get out by making this slice. Just to break this into a little bit cleaner steps, we'll say my list equals this list. I'll print it out so we can see the whole thing. And then I'll print out my list and that slice from -2 to the end. For the second exercise, we're asked to take that same list and select every other element starting with the very first one. So that would be 0, 2, 4, 6, and 8. For this, we'll slice the list from the beginning to the end, taking a step size of 2. So we got out what we expected, 0, 2, 4, 6, and 8. We went from the beginning to the end, picking out every other element by taking a step size of 2. Finally, the third exercise asks us to print out or select every other element, like we did in exercise 2, but starting with the second element. Recall that Python is 0 indexed, so the second element is in position 1. Then we'll slice to the end of the list, taking a step size of 2 to get every other element. This gives us 1, 3, 5, 7, and 9. So we got every other element, but we started with the second element instead of the first. You may remember in the lecture on variables in the PyProgramFlow notebook, I mentioned there is a distinction between variables and names. Variables are objects stored in memory. Names are what we use to refer to variables in code. Here, we create a variable that's named A and assign it the value 4. We then create a name B that is equal to the name A. Notice that if we reassign A, this creates a new variable that has the value 5. So A and B have different values. The reason this reassignment changes the value of A or makes a new variable is because integers are immutable objects. So anytime we assign a name or make it a variable assignment with an immutable object, we create a new variable. Let's see this process again using Python lists. Here, we create a variable A and assign it the value of this list. We then have the name B equal to A. We then take A and mutate the list by changing element in position 1 to have the value 5. We find that both A and B have changed. The reason is that A and B point to the same list object in memory. They point to the same variable. When we mutate that variable, we don't create a new variable. So B points to this same list that we just mutated here. This is an important kind of property of mutations compared to when we're working with assignment, where we're assigning different values. Note that if we had this code, but had A equals 3, 5, 1, then A and B would be different because we've assigned a new variable, this list, to A. So this is one illustration of a case where we have to be careful when dealing with mutable objects. If multiple names point to the same variable, and that variable is mutable, and we mutate the variable, that change will be reflected whenever we invoke a name that points to that variable. To conclude the video, I'd like for you to try and explain the difference between a name and a variable. I'm going to go to the discussion board and create a question for this exercise. When you've thought about an answer, feel free to share your answer here on the discussion board. And I should make sure while I'm here to tag this question with the appropriate tags. Data structures, mutation, variables, or variable. Okay, so when you have an answer, please share it here. In the next video, we'll talk about the data type tuple.